Welcome back, everyone. In this video, I will be finishing up the section on areas and distances. This is really the main last problem, and we were sort of in the middle of it, but we kind of developed a formula that wasn't related to our specific problem for plugging in xi. So this is our formula for the Riemann sums. And in general, we would have to go through when we were approximating. Let me go back to an example in a couple videos ago. When we originally estimated the area under x squared from 0 to 1 using 4 rectangles, we went through and did the left and right endpoints, but we had to figure out the x values to plug in and then do it manually. Because in Riemann sums, we want our formula, oops, I scrolled too far. We want our formula in terms of n. We have to make sure we don't actually plug in or try to plug in the x values specifically. We want to plug in the x values with a formula. And that's what we did last time. So just remember, this is if your a equals 0, which is your starting point. If your a does not equal 0, you have to use this for xi. But these will always work as long as the base of the rectangle is equal. So they're all the same, and you can always assume they are the same because you're the one that's estimating the area. You're really making the formula yourself. All right, so now what we're going to do is we're going to take our Riemann sum formula with our right endpoint formula, which is what we're going to plug in for xi there. So let's go ahead and just underline that in red. We're going to plug in what xi is. Then we're going to go ahead, plug that in with our a and our b. So b is 1 and a is 0, and see what happens. All right, so we got the limit as n goes to infinity, the sum from I equals 1 to n. b minus a is 1, so this is 1 over n times, and right for the time being, I'm just going to plug in what xi is. We do have a formula for the function, but I don't want to do that yet. So we got f of xi. Well, xi, we have I times b minus a over n. Now, if you're doing, one thing I'll mention here is that if you're doing any function, Riemann sum from 0 to 1, or the exact area, means the same thing, from 0 to 1, this is actually a formula because we haven't used x squared yet. And that could be pretty helpful if you're doing a different problem where the area under the curve you want to find is from 0 to 1. You can just kind of use this formula, plug in your function value, and go from there. All right, so what do we have now? Well, I'm going to take what f of x is. Actually, you know what I didn't do in the previous step is I didn't plug in what b minus a is right here. So let me go ahead and do that. So xi was this. We had I times b minus a. Well, b minus a we figured out was 1 over n. And that'll just make it easier when we plug in what f of x is. So we got 1 over n, and then f of x is x squared. So the x value we're plugging in is just I over n, because it's I times 1, which is just I over n. So we get I over n squared. Okay. So that's our function formula. If you had f of x equals x cubed, then this would be I over n cubed, because we're just taking the function x value and cubing it. If you had sine of x, then this would be sine of I over n. So now how that works. And then we do the limit as n goes to infinity. Again, we haven't done any limits yet. I equals 1 to n. Forgot to write the n up there. If you square this out, we have 1 times I squared, which is I squared on the top, times n cubed on the bottom. Right, and now this is where dealing with limits and summations and maybe not being very comfortable with them yet is going to maybe look like I do a trick that you're not allowed to do. So let me go ahead and show you something. Right, so the first thing is that when you do a summation, the letter here that is called your index. It's a variable. The only variable inside that matters is I. So that means this I squared must stay in. This is called your index, as was mentioned about in the kind of the preliminary video. So that must stay inside the sum, but you can actually bring this in because it's not I. You can bring this outside. Now it is in the denominator and we can't bring it outside the limit because it is an n, so it has to stay inside the limit, but we can bring it outside the sum because there's no I there. So we have the limit as n goes to infinity of 1 over n cubed times the sum from I equals 1 to n of I squared. And now what we have here is this thing has a formula, and I have a little cheat sheet below here. Let me go ahead and just scroll down so you can see it. These are the useful summation formulas. They're basically the summation formulas when I goes from 1 to n of I squared, and I cubed. These aren't necessary to memorize. That's why I gave them to you already. But we're using I squared. So what you want to do is just go ahead and plug in the formula we have there. The one for I squared is n times n plus 1 times 2n plus 1 over 6. So I'm going to go ahead and do that. What we have there is exactly what we were talking about. So we're going to plug it in. We have the limit as n goes to infinity of 1 over n cubed times, and then a fraction here was n times n plus 1 times 2n plus 1 over 6. Right? And you can simplify this as one fraction. So we got the limit as n goes to infinity. We have 6n cubed on the bottom. Now what you want to do on the top, it's up to you. You can kind of analyze it, or you can actually multiply it out. What is n times n plus 1 times n plus 2, or 2n plus 1? Well, you can distribute the n to the n plus 1, so you get n squared plus n, and then multiply it by 2n plus 1. And the reason I'm doing this is because this is a limit as n goes to infinity. If you remember how to evaluate those, which you should, we want to compare the largest powers, and if it's the same, we have a formula for that. If the bigger power is on the bottom, we have a 0. If the bigger power is on the top, we have infinity. Since this is an area, it makes sense that the powers should be the same. We should get some number that's not 0. Let's go ahead and simplify some more. We still have 6n cubed on the bottom. Now on the top, we have n squared plus n times 2n plus 1. So go ahead and FOIL that out. N squared times 2n is 2n cubed, plus n squared times 1 is n squared, plus n times 2n is 2n squared. And let me correct that exponent there. That should be a 2. And then finally, plus n times 1 is n. And you can simplify this further, but we can see the largest powers on the top and bottom match, and they're n cubed. So according to our limits at infinity, this equals, since they're the same power, same largest power, we just look at their coefficients. On the top, we have 2. On the bottom, we have 6. This is 2 over 6, or simplified to 1/3. Once again, I want to go ahead and just mention that what we did in the last video wasn't really specific to this problem. We developed a formula for you to be able to plug in an xi value. This stuff is really the work for this problem. But yes, there is probably a lot here. One thing I always like to mention when I teach this sort of thing is that this isn't the way we're going to be finding area going forward. The point is, just like with the derivative stuff, like I mentioned at the beginning, we really want to make sure that you can really appreciate and also understand that when we find areas under curves and things like that, this is going on in the background and we are able to skip it because of how everything ends up working. Right? But we did just figure out something very interesting. You just figured out that this area, so I'm going to bring this back in, the area from 0 to 1 under x squared, this area is actually 1/3. This isn't a triangle. This isn't a circular thing. It's really nothing you could have found the area from before. Now going forward, hopefully we will have a much quicker way to do this because that took forever. But the point is, we now know at least how to do this, at least in a complicated way, but we can do it. And we will develop ways to make it a little bit easier for us. So I think one of the more realistic types of questions in this section is not so much actually finding the area like that, but And it is good practice to be able to do it because you have to set up everything. But really, if you can look at a limit like this, knowing what area you're finding. So number 2 here won't be nearly as much work. What we want to do is we want to look at this limit and determine a region whose area is equal to the given limit. Now, we're not trying to draw it or anything. What we want to do is just describe what this is saying. What is A, what is B, and what is f of x? So let me go ahead and write that. We want what is f of x. So what is the function we're finding the area under the curve? And on A to B, so what is A and what is B? Well, there's actually a pretty quick way to do this. And it really comes from what happens when you, at least for A and B, it comes from what happens when you go ahead and plug in something. So remember back when we were deriving this formula, what we talked about was that really it's starting at 1 over n for our formula for the right endpoints. Well, as n goes to infinity, 1 over n goes to 0. So you should know that. The limit as n goes to infinity of 1 over n is 0. So the idea is when you actually plug in I equals 1 and you take the limit, you actually get the a value. So a is the limit as n goes to infinity. And what we're talking about by plugging in I equals 1 is we're talking about plugging in the x value here. So we plug in I equals 1 for a because that's our starting value, and I equals 1 is our starting I. We got 1 times pi over 3 times n. And now you evaluate this limit, and this will give you the a value. Well, this is just pi on the top. Oops. Don't want to forget my n limit. I just want to rewrite it without the 1 there. And this is just a number on top, so pi over 3 times n. Well, the bottom has a variable of n in it. The top is just a number, so this is a number over infinity, which is 0. So this actually starts at 0. And pretty much all the time, a is always 0 just because it's the only way to realistically do these things. If a is not 0, this becomes a huge mess. All right, now to figure out b, it's very similar idea, except you're not looking at the starting value, you're looking at the ending value. What is the last value of I we're plugging in? It is n. So we want to take the same thing and we want to plug in I equals n for b, and we do the limit as n goes to infinity. We've got, when I is n, we get n times pi over 3 times n. And now you evaluate this limit. Now this one we can do the same way. We can match the powers, but this is even a little easier. I'm going to go ahead and rewrite it. N times pi over 3n. Because we don't have any pluses or minuses on the bottom, you can just cancel the n's out just like that. And what are we left with? We're just left with doing the limit as n goes to infinity of pi over 3. Well, we know the limit, taking the limit to any number of just a number is always the number. So b is pi over 3. And now this might be even the easiest part, is actually figuring out what is f of x. You may have been able to guess it, but you just look here. This is your function because this is the b minus a over n in front. And this function here, this is f of x by replacing the entire inside with x. So this is actually the formula that we derived here. Xi is I times b minus a over n. But what you can really do is just say this is going to be x, with the exception of if you see any weird exponents or something in here, then maybe not. But there's nothing going on. This is just b minus a over x. So f of x equals sine of x. And what this is representing then, this is representing the area under the curve of f of x equals sine of x on the interval 0 to pi over 3. Probably the easiest thing to not notice here is that, or make a mistake here, is that you see this thing in front. If you don't want to forget this is b minus a over n, You don't want to think that's like an x or something. This is not x times sine of x because you would need an I. I is really the thing that's telling us something about x is happening. Okay. Once again, that's probably a more realistic thing, just to realize that this limit is representing an area. But that is the end of the section finally. I know it's a pretty long section, but it's very important because it's really the start of bridging our area under the curve to the antiderivative together. And it will come together in a much cleaner way in the future. And I will see you in the next video.